do everything.
Welcome to the seminar of School of Socioeconomic Affairs. And today our guest is Roger Laws from CSIRO, and his partner is Mark Lorenzo, apparently. And his talk is either with to new technology, to old technology, modeling crop rotation with land use sequence optimizer. So you have 35 minutes, and we have 10 minutes for questions.
Fine.
Okay.
No worries. Look, thank you everyone for the invitation to give a talk on crop sequencing. Crop sequencing is an area of agriculture that myself and Michael Renton, who's also been in the audience, have been involved in through CSIRO and with the GRDC for probably 4 or 5 years. And when we got involved in it, we sort of were scratching our heads a bit, because it's the sort of problem and concept that everyone's taught in their first year of an ag science degree. You rotate the crop to prevent disease build up, and you might provide nitrogen through a legume. So why is it a topic of interest in today's world? And I guess with that in mind, what we did was we looked at, well, why are we discussing this? The whole notion of crop rotation in Australian agriculture has changed. We used to have the lay farming system, so a cereal crop grown in rotation or sequence after lay pastures, typically subterranean clovers in Western Australia. In the eastern states, it was something like meadow pastures. But that rotation disappeared, largely because livestock became unprofitable. And in other regions, crop sequences like wheat and canola emerged as the dominant crop sequence, where canola was highly profitable, wheat was highly profitable. The two could be grown together, and in some cases that seems to have been a very good system. It dominates throughout parts of Western Australia, it's common in South Australia, it's common in parts of New South Wales and Victoria. So the question with that particular sequence, is that a risk? Or alternatively, is that actually the optimal economic choice given farmers' experiences in those regions? Just to give you an idea of how quickly the trends in crop sequencing and crop rotation can change, this is some surveys that we did here in WA around the Mora region, just looking at what crops were grown prior to wheat. And as you can see, at the turn of the millennia, most wheat crops were grown following something other than wheat. But by the middle of last decade, that had jumped to nearly 30%. That's that black line there. And that coincides with a similarly spectacular decline in the number of wheat crops grown after lupins, which were at nearly 50%, and it declined down to 15 to 20% again by the middle of the last decade. So we're seeing this dramatic shift in the sorts of crop sequences farmers are adopting. So the question then arises, well, how do you evaluate the economics of growing a break crop? What are the components to that? So we have to capture things like the cereal yield, the break crop yield, two very vital components, the prices of both of those two products, as well as your nitrogen fertiliser price, and also the capacity for the two factors that dictate why you might change a crop, which is what are the weed population dynamics doing, what sort of stress is coming into the system, and also what are the disease population dynamics, what are they doing? Are we getting increases in things like rhizoctonia, take-all, or all these other factors that might compromise your capacity for your cereal crop to grow and be profitable in its own right? So we want to capture all of these different processes in a modelling framework. So Michael Renton and I sort of got together and had a bit of a chat about this, and together we constructed what we call LUSO, the Land Use Sequence Optimiser, which is a bioeconomic model of weeds, disease and nitrogen. It can be thought of as a state and transition model, where the states are each year, and in the first year what you have is a starting weed population at the top. You'll have a disease population to start with, and you'll have a quantity of nitrogen present in the soil. We set all those parameters up in the model, and they combine and give you a crop yield of some description. Basically, if there's very low levels of those stresses, you get a high crop yield. if there are high levels of those stresses of weeds and disease, you will compromise crop yield. As you choose a particular crop, that's going to flow through and affect the outcome in the following year. So some crop choices may lead to an increase in weeds and disease, and that might then also require more nitrogen fertiliser, leading to perhaps a lower crop yield. And then again, if we continue into a third year, we might wind up with even more crop weeds, a greater disease problem, a higher nitrogen requirement, which might lead to a further reduction in crop yield if you choose one particular management action. Conversely, you might change the crops and alter any of those dynamics. And this model is structured so that you can run a sequence for as long as you like. If you wanted to look at a 20-year run, you could with changing crops and pastures. You're able to set the crop choice and evaluate the outcome. To give you an example of how this might work, what we have here is a run set up for coconut in WA, where if we look at 5 wheat crops in a row in this, the light blue line, what you can see is the weed seed bank increasing at an almost exponential rate, particularly after the third year. If you compare that to putting in a lupin crop, where you're able to manage the weeds control, you're able to suppress that seed bank and alter the seed bank dynamics, which will in turn alter the economic outcome for that rotation. You can further do some more damage to that weed population by introducing a grazed pasture into the system. And this is just an example of the sort of dynamics that the modelling framework allows you to capture. In doing so, what we do is we have to set the yields and pricing scenarios for each of the crop sequences. And not only that, we can play with it. So in this example in coconut, we actually set up 3 different wheat scenarios where we might run an expensive wheat crop where we apply lots of herbicide, we apply a lot of fertiliser to it and feed it to target a high potential yield. Conversely, we might then try for a low wheat yield or a lower wheat yield by reducing our input costs and accepting maybe that we get a lower yield as indicated here. So we can play games not only with the types of crops chosen, but the resource inputs that you might consider for those crops. You then repeat the process for canola, lupins, pasture in this situation, and also if you want to include something like a fallow, you can include that into the system. We can then bring in the nitrogen requirements and the disease requirements. These are basically factors that we can derive experimentally, and this has been really enlightening because when we challenge a lot of our agronomic experiments and say, provide us with the information on weed population dynamics and disease population dynamics, we really struggle. And it's been one of the great foundations for this model by challenging conventional agronomists and saying we need this information to do the economics properly. And we've been unable to satisfy that requirement in many situations. But we can set the parameters up nevertheless with best guesses and expert opinion. And once we do that, we capture what the yield loss due to particular biotic stresses might be through time. So this is again that cogenup analysis where we didn't use the optimizer, we just used it as a calculator to track what might happen to the weed populations through time. So you can see that your weed populations might generate a yield loss after wheat and after canola. Conversely, after a pasture managed explicitly to obliterate the seed bank, you might keep the weed population low and as a result reduce the yield loss accordingly. You do much the same thing with disease. You can track that disease population and that disease will then damage crop yield, and we can see that different crop choices will then influence the damage that you'll experience in the wheat crop. And what we tend to do is then combine those 2 biotic stresses, weeds and disease, and look at the combined damage with percentage yield loss. So we might have, for one scenario, you can see how we're losing nearly 30 to 35% of cereal yield as a result of your combined weed and disease biotic stresses. So we can play these games across a region and look at what might be the optimum and then calculate that accordingly. And I think one of the challenges with crop sequencing is when you look at the agronomic experiments that have been run Australia-wide for forever really, a 0.5 tonne to 1 tonne yield loss through different break crop options is really common. Something like 160 odd experiments have been run in WA and reviewed quite recently, and the average benefit from growing a crop after a break crop is about 0.6 tonne. Did the same in South Australia, it was about 0.7 tonne. In New South Wales, it was 0.8 tonne. It just keeps coming up a number like that, which equates to the sort of yield losses that we're indicating in this graph. So when we put in different crop rotations, what sort of yields are we getting? This is how this half tonne might manifest itself. It's with changes in weed and disease populations. So we're getting that half tonne break crop effect by managing weeds and disease. One of the interesting things that we look at with farmers, and when we go to them and suggest that they should consider a break crop, often the first response is, I'm not prepared to lose money in a given year. And it's like, well, what about the future trade-off? So the farmer's telling us that there's clear opportunity cost from not growing a wheat crop in a particular year. And then we say, okay, fair enough, but what about the future outcome? How do we track that? And this is, again, the example that we have in Kojana, where we looked at a loss-making pasture. We deliberately set this up to give a very negative impact in terms of it was a highly managed pasture. We focused entirely on managing it for a future crop. We didn't worry too much about livestock returns. We focused on getting legume content into it, and we also focused on basically obliterating the weed seed bank. By increasing that legume content, what you're doing is you're probably saving yourself some nitrogen in the following year, but you've got to manage the pasture accordingly to do that. And then what we see is a massive profit on offer in the following year in that pasture wheat rotation. In the third year, you still get to make some of that profit. The canola wheat scenario is quite different because the canola is a profitable crop in its own right. And the irony is if you have a break crop situation where the break crop does everything a break crop should do in terms of managing weeds and disease and is profitable, well, that's the goal. That's what you're after. If you've got that available, great. This is all fairly easy. But in many situations, people might be frightened of growing a crop like canola, particularly as you move out east. For a minute, I forgot which state I was in. So anyway, that can alter whether someone is prepared to grow a particular crop. But then if you look at your continuous wheat scenario, which in many parts of Australia is what farmers are doing, we're coming across paddocks that have been in wheat for 7 years. This is not unusual. They're making their profit in their first year and they're just experiencing a slow, steady decline through time. And that's captured in this cumulative graph here, where most of the profit's made in year 1, slight decline in year 2, which with seasonal variability you probably wouldn't notice, and by year 3 you're perhaps below what might be a profitable crop. To give an extreme example, we were looking in the Victorian and South Australian mallees. Crop yields were down to 1.4 tonnes per hectare. The local farmers were happy with that crop yield. They were perfectly happy with it. They thought that was normal. That's how long this continuous wheat scenario had played out. It had changed their mental perception of what they thought was acceptable. With a couple of break crops, we increased crop yields by 1 tonne a hectare in a sub 300 mil rainfall environment. It's almost a 50% yield increase. So that's how serious and insidious this continuous wheat rotation can become, just with this gradual alteration in what farmers perceive to be an ideal sequence. One of the things about this, and we always get challenged with, is, well, hang on, it's all very well to just do this in a deterministic form, use averages, use average losses, but seasons vary from year to year. How do I cope with that? Is one type of sequence more risky or more variable than another? If I choose not to grow a wheat crop and fallow it for argument's sake, or grow a pasture, am I going to lose out? I'm frightened of losing out. It's a mental process of thinking about that fear of losing by not growing a crop. So to address that, we took the LUSO model and we made it, we now call it LUSO VAR, which is effectively a stochastic model. So we can, instead of just taking one wheat yield for a given year, we can draw from a distribution. And not only that, we can now match those distributions. So we can compare one set of crop sequences or rotations with another from an identical set of seasons. So we can effectively do rotation shootouts, but over different sorts of seasons. So we might pick a couple of drought years, we might pick a couple of wet years, and then see how that process unfolds. So what we see in year one for that Kogenup example I get, we have on the top line, we have canola profit, which is the blue chart. We then have pasture profit, which you can see we were making a bit of a loss, which was how we set it up initially. And then we have our profit with our wheat crop and the distribution of all of them. By the second year, you can see we have this dramatic range in profit as a result of the pasture. Often that red line I have set there is at $200 a hectare as a profit. The canola profit also gives you quite good ranges, but we can see our wheat crop, we're now starting to get a lot of profit that's only around $200 a hectare. We're losing that profit in very good years. And then this just continues as you keep going with wheat. Your capacity to get these high profits have just about disappeared from the system once you've been growing wheat continuously for a period of time. And then when you combine the distributions from all those 3 years, the big thing that we noticed with the sequences and the distribution was this loss of high profits in favourable seasons with continuous wheat rotations. So what we'd done, we'd reduced the farmer's capacity to capitalise on favourable seasons with these continuous wheat sequences. Now, and by doing that, by taking away the farmer's opportunity to really capitalise on valuable years, that's actually when they make all their money. So they've created a system that doesn't let them make money, even though they did it because they were frightened of losing money. So it's this tautology that we're trying to deal with and able to highlight with this sort of crop sequencing model. To take this further, these were short runs that we did, and we didn't use the optimizer in this situation. We just looked at canola wheat, pasture wheat, and continuous wheat. In contrast, we wanted to look at a longer term crop sequence, run it for 10 years. We could have gone even longer, but we figured that 10 years was long enough to see if there were emergent properties and trends in the way the crop sequence would operate. This thing is set up to be discounted, although from a biological perspective, the whole concept of discount rate and how you discount these is actually a really nice conversation to have maybe after, because it does interesting things to a crop sequence if you set discount rates at certain levels. Again, the yields are drawn from the absent distribution. And then what we said was, hang on, not only are the yields drawn from a distribution, but we need to draw the disease. We know that disease is going to vary with the type of season you get. We know that with the drier seasons, that we tend to have less of a disease problem. So we don't just want to assume we have a bad run of disease in low rainfall years, because we tend not to. The nitrogen requirements, well, nitrogen driven by crop demand. So again, we need to scale that nitrogen requirement to the demand of the crop. And then finally, what do weeds do in good and bad years? When we start looking at the weed population dynamics literature, there is very little on how those weed population dynamics change from season to season. We were quite staggered and went, okay, well, this is a real gap, because that means how do we manage after a drought? What have we done to the weed population just through natural processes? And to be honest, even with the disease population dynamics and relating that to season, we've only been able to source that from one manuscript. So on top of that, we then said there's a lot of uncertainty around these processes. So much uncertainty that Michael and I decided to introduce some random error into the model, which we can scale, because we said there could be some uncertainty there, we'll just let it rip. And so we can scale up that uncertainty if you so desire. So after running the optimisation, and this is in a Birchip scenario in Victoria, I won't bore you with the in-depth parameterisation of each coefficient. We'll be here till Christmas if I do that. But basically, we wound up with a 10-year sequence where we had field peas, canola, wheat, field peas, another wheat, a couple of pastures, canola crop, wheat crop and field pea crop for the optimal rotation. And then we had some agronomists from the region give us what they considered to be their ideal sequence. What would they do for that scenario? Don't worry too much about the format. This is not about here is the optimal sequence for this region. That's not what this talk is about. It's just to give you an indication that other people certainly will have views on what the ideal sequence is, and what they are doing in their mind is effectively trying to manage the biotic stresses anyway and trying to do what LUSO is doing for them. So they're doing that in their head. And so it's asking, well, this is how they think that those rotations they gave me were managing weeds and disease and making profit for the farmer. And then we did this where we said, can you manage weeds in the cereals? Or conversely, can you not? And all we did was say that weed control in the cereal was no better than it was in canola, versus the weed control in wheat was about what we think it is. There's only a 2% difference in weed seed survival. It's not great. It's a very subtle shift. It's a very important shift though, as will become evident. Looking across the sequences, we didn't change any of the disease parameters, and disease in these situations is not important. It's doing no more than reducing yield by about 4% in any of the scenarios we looked at. So everybody's managed disease. Every scenario has managed disease. It's not an issue. Weeds are a completely different story. So what we have in this situation, where we have, if we just focus on what I call the poor line, that's where the weeds can become a problem in a cereal crop. You can see both the optimal rotation and the rotation agronomist B suggested kept that disease population under control. Conversely, the two scenarios, which was agronomist A and agronomist C, those weeds became an incredible problem very quickly as a result of that scenario, because the weeds couldn't be managed. Once we shift that and say those weeds could be managed in a cereal, and again, the biological shift was small in a biological context, the impact on those two rotations was enormous. It drastically altered the seed bank dynamics, which gives you a good indication of what agronomists think how well that those wheat crops are operating in that environment. It's a really good insight in a way of using the model of saying, well, how do you think the world works? And they think they can control the weeds in the wheat. So surveys like Rick Llewellyn's would suggest that to some extent they're right. So perhaps suggesting weeds can get away in wheat crops, don't know. It's a really good question. Again, this is just looking at the seed bank additions. They're shooting through in those same two rotations, so the whole thing sort of follows each other as you'd expect. And then when we start looking at the profit of that 10-year sequence, well, the optimal profit one, not surprisingly, well, it should by definition, and that recommended by agronomist A and agronomist C, as a result of those seed banks dynamics, started losing considerable amounts of money. But when we shifted that, when we changed that weed control, we can see that particularly the rotation suggested by agronomist A, that improved enormously. And what's more, the standard deviation around that, or the variability in profit from year to year over that 10-year time frame, also dropped considerably. So the rotation agronomist A suggested was actually, to some extent, less risky on a year-to-year basis than that from the optimal rotation. The others didn't do quite so well, but nevertheless, they certainly improved considerably as you develop that capacity to manage weeds in a cereal crop. So when we look at that profit breakdown from year to year, you can see how that standard deviation varies. We have a period with the optimal rotation where it's basically managing the weed seed dynamics, whereas with the others, with the local agronomists, they were suggesting managing the weed seed dynamics and the disease more frequently. And the other agronomists took more extreme takes on that. So there's basically what you've got is different ideologies and different takes on much the same concept. The thing about the optimization model is it can time all those things perfectly because it has perfect knowledge. And that's the difference between what an optimization model is doing and what an agronomist is doing in the field. The agronomist is guessing what the weed seed population dynamics is doing, what the disease is going to do, and is making a decision accordingly. the optimisation model can get it right, at least in its world, and as a result can basically maximise profit. When we start drawing from the distributions and we look at how different those different sequences are over time, what we're finding with those, definitely with the agronomous sequences, many of the sequences are generating negative returns. And not only that, all sequences have negative returns at some point. Anything to the left of that dotted line around the origin is losing money over a 10-year period. And even the optimum, the black line, was losing money in about 10 to 15% of seasons. So it didn't matter what you did. If you got a bad run of seasons, it doesn't matter what your rotation is. There's nothing you can do about it. When we've got better weed control in that cereal system, things improve enormously. And it's a really important finding, is that by keeping on top of those biotic stresses and having the technologies to sort of enable people to crop successfully, you make huge changes to those distributions. Now, most of the crops, most of the sequences, it almost doesn't matter. They're all generating profits most of the time. The difference between those two plots is enormous. And not only that, the optimum's not always optimal. And there's a reason for that, which I'll just discuss quickly in a minute. But basically, it doesn't matter what sequence you choose, you will often get a profit. And the difference between those sequences declines as the biotic stresses disappear out the system. It's as simple as that, really. And not only that, the optima doesn't always win. This is just indicating when we had poor cereal weed control, the optima does win, but as that cereal control of weeds improves, the optima and getting the optima is nowhere near as important. So why did the optimal sequence lose? It sounds tautological, but this is a deterministic optimization. It's not optimizing a known set of seasons. So if we knew what the next run of rainfall records were going to be, we could actually run the optimization around that, but we don't. We just take an average and then say that's the optimal. What happens if we draw from a particular year? Whenever you look at a series of runs, what you'll see, and you compare two different crop sequences, many of the years, they're quite similar. There's not a lot of difference. But occasionally, and I've highlighted it, the optimal might have a high profit year and the other sequence might have a low profit year. But if that was a drought, you've lost that high profit year out of your sequence. So if you have two of those failures and then again, conversely, a successful or a really good year where your other sequence is not doing anything, that will then flip which one is going to be optimal for that particular run. And that's why you get that difference in outcome. And it's just because of that probably suggests don't all run the same sequence across your whole farm. So really, what we're finding is that crop sequencing is really important when you've got biotic stresses in the system. It's really important to know what those biotic stresses are. And what we're finding is that our knowledge about the seasonal impact on those biotic stresses in a predictive sense is probably not good enough at this point in time. If we were to envisage where we would take this work, it would be about saying, well, how do we get better at predicting those stresses? Because there's a big difference between managing those biotic stresses, which the agronomists were doing, and you can almost overemphasize that at the cost of making a profit. And that's the sort of thing that we're trying to do with this optimization. It's trying to time that period of profit making with this period of rehabilitating the landscape. That's the game we're trying to play and get it as close to optimal or right as possible. And what we're doing ultimately is using an optimization model to develop trigger points for management action. We're not expecting the industry to go out there with an optimization model and play these sorts of games. It's too big an ask, it's too fiddly a model to use in that context. But at what point do you need to make an action? And it's not too hard when there are plenty of break crop options. But if all you've got is fallow, and you've got to make the decision to fallow instead of growing wheat, then this question about when should I fallow becomes very important, and getting it wrong in either direction, either too conservative, so too many fallows at a point in time, or conversely too late, will be very costly to your operation. So that trigger point can be finessed with a model such as this. We're also assuming from the simulations that farmers are just as likely to hit yield potential with canola and field peas and chickpeas as they are with wheat. That's a pretty bold assumption. It's a very bold assumption. And I think that's one of the issues we've got with our break crops. We don't know enough about the physiology of our break crops. If we compare our knowledge of wheat and how well we can predict wheat in a given climate compared to how well we can predict chickpeas and what farmers are going to get with their chickpea crops, they're chalk and cheese. And that's another form of risk that we haven't explored with this model at all at this stage. All I've done is taken the APSIM estimates of chickpea yield. And I guess that's really my next point, is are canola and field peas, from the farmer's perspective, more risky to grow from that ability to achieve yield potential? And the model says not really, but I think if we asked any farmer, they would disagree with that comment. And yeah, finally, the seasonal effects on disease and weed population dynamics are not well understood at all. For asking the literature to help parameterise this model, we've had a lot of trouble. So we're now retrospectively trying to get that information, reanalysing old experiments using different statistical techniques to try and gain that understanding. But hopefully we'll be able to do that better. And by doing that better, we then hope that we can get these trigger points more tightly defined and more precisely defined for different regions, for different soil types and following droughts and good years and bad years. And that's why we want to be able to do this last dot point a lot better, so that we can use the model and identify what those trigger points are. Thank you.
Just a quick question. So your measure of profit, I suspect, is a gross margin?
Effectively, yeah. It's got fixed costs in there as well.
It's
So
got
we-
fixed costs. Okay. So, and do those fixed costs vary?
No, we've kept them stable from year to year, but
Okay, because obviously that's another story, that if you go to
Absolutely.
farm size and you change the fixed cost component, then your land use
absolutely.
is going to change.
Just your second last point about canola and field peas being more risky to grow and stuff. I think maybe another consideration there, not so much with canola, but things like field peas, is that they're potentially more price risky. There's
Absolutely.
less options available to hedge
Sure.
your prices and that sort of thing compared to wheat and canola.
So a component of the model that I didn't talk about at all is that we have a price mechanism in there as well. So we can actually explore the stochastic variability of price as well if we wanted to. It's just in terms of teasing out a biological message, you've kind of got a fixed price, because price actually swamps everything. As soon as we put that in there, it blows all the biophysical processes out of the water, which is a whole nother presentation in its own right. Because it doesn't matter if you put wheat at $400 a tonne and you lose 40% of your yield through disease and weeds, still might not matter. Still might be the most profitable thing to do. So it just depends how you're playing that game. But yeah, absolutely, I take the point.
Just another question. No, you go.
Right. My question may be a little bit naive. I'm not a modeler, I'm a statistician. But to me, I understood the whole concept. You use the stochastic model, you got the distribution, you're playing the different scenarios by changing the parameters. But I've been analyzing maybe for the last 20 years field experiments with different crops, Western Australia and Australia-wide. And I just cannot understand the concept behind the modeling. So in order to get your model, I presume you use some huge data sets to get the idea. I mean, you presented some plots. Now, I witnessed in Western Australia, for example, such huge GYE effect, which you can have variety while catching. So there are two issues with the model form. First, different varieties respond, wheat varieties, for example, respond in completely different way even at the same location,
Yeah.
right?
Yeah.
To weeds, to
Sure.
many other things. That's
Yeah.
one thing. And I think the model is losing this. We're talking here about genetic effect.
Sure.
Separately, we have environmental effect. The same variety, wild catching, can
Yeah.
be tons higher
Yeah.
in terms of yield
Yeah.
than in lower rainfall in high rainfall, right?
Yeah.
So basically, I don't know how this model is able to capture this. That's first issue. Second issue, you mentioned other crops. I can tell you from my experience, and I can order the crops in order their variability.
Sure.
The less variable is wheat, followed by barley, lupins,
Yep.
field pea, chickpea, and so on and so on. So, could you please explain, because you
Sure.
mentioned
Sure.
cogena.
So,
So, what kind of data you use
sure.
to derive your model?
So the Epsom model will do E really, really well. Very well.
Which model?
And the Epsom model will do E very well in the way you just explained it. It will capture it really well. So the crop simulation model Epsom will grow a crop in terms of rainfall and soil and capture sunlight and CO2, and it'll capture all those processes. I'd expect to simulate E with about 90%, 95% accuracy, particularly the relativities, if not the absolute values.
But the plots you presented were like general plots for wheat or for crops.
Sure,
I
sure.
mean, they were too
Sure. There is a
broad. There is no, a farmer wants to know. I have this piece of land because I was exposed to NVT trials. That's what they want to know. If I grow well catching, how much tons per hectare I'll get. If I grow this, how much? So how you are going to address his concerns with this model or the rotations?
I mean, the other thing is the genetic differences within wheat are not that great relative. I mean, I know they are. Like, I'm doing GYE work as well, so
Absolutely, one gene can be unlocked by one environment,
Absolutely.
and you can see absolutely completely different performance of the same variety
Absolutely.
now, and particularly Australia.
I mean,
It's such huge content. It's not you.
Yeah, my question will be very brief. The loop in wheat rotation, then why that is failed? So
why?
yeah,
Sure.
so we got a perfect example where in the northern agricultural region,
Yeah.
okay, some of them were very close. The weed build up in lupins, for example. So can you give some
Sure.
insight?
There's two reasons why lupins failed, which I'm sure there's enough people in this room that know why it was. Which weeds was one, and a set of herbicide-resistant weeds, which depending on how we set the model up will reflect that. And the other one is lupin price. Lupin price is at $200 a tonne. Who cares?
But you mentioned that it doesn't matter if you look at the 10-year term, if it does reduce the root diseases or fungal diseases. If we can get the weed control right, then the fixing the nitrogen, which is quite better than canola. So can we show in a 10-year frame instead of field feed?
So what you would do to look at when lupins would come back into the sequence, I'd play two games with this model. I'd firstly look at our capacity to manage weeds under lupins. So you could do that through farmer surveys, through specific agronomic trials. The second thing I'd be looking at is what are the yields we're getting with lupins, with the current lupin varieties. And I'd also be looking at the price of lupins. And at some point, lupins will come back into the system. If lupins hit $500 a tonne tomorrow, they'll be selected.
It won't.
No, I know, but that's the point I'm making. There will be a point where lupins will re-enter the system, and it will be driven primarily by economics, more than the biotic processes.
Just a quick question.
Yeah.
In looking at pasture,
Yep.
how did you describe the gross margin on pasture?
Badly.
Probably answered my question.
What do you do with the discount rate?
At the moment, we've just got it set at, well, I set it for 0 for this particular run deliberately, but we can set it at just a nominal 5%, 7%, whatever you like per annum.
And what does it do in terms of those comparisons?
What it will do is it will, if you play games with the discount rate, what it will do is it'll set the period of exploitation of crop early on, and then it will rehabilitate later. That's what will happen if you play games with a discount rate. If you don't, it will balance it more evenly over a 10-year run.
So is that explaining, going back to your first point of saying you've seen people with these very long runs of week,
Yeah.
is that basically the economically rational? You started saying it's economically rational.
Yeah.
Is this model telling you that that's basically what they're doing is economically rational? And
It's a really good question. Michael and I built another component of the model where we ran the optimization over 10 years, but we've got another version of it where we can run the optimization every 2 years. So you're optimizing every 2 years, reset the parameters, go for another 2-year run. And they do pick slightly different crop sequences along the lines of what you're talking about. But yeah, the argument is, are farmers just profit maximising every year? Is that their management goal on every paddock across the farm? Don't actually know the answer, but that's...
Some farmers will have very high discount rates.
Mm.
Just a very quick one here.
Yeah.
I'm just a bit curious on the biological side.
Yeah.
The fact that we know very little of seasonal effects on the on disease and so 2 questions there. Is there any work done in other areas of the world, United States, I mean other Mediterranean climates that you can draw on? First question. And second is, does it matter that much? Because you're really interested in the cumulative aspects. If you look at the cumulative aspects, in fact, the seasonal effects will probably dampen themselves over time. So maybe, I don't know.
Good question. I mean,
And you could probably simulate that and then realize that it doesn't really matter that much.
good question. Something more for me to do, really. Yeah, absolutely. I know the French have a take-all model, which, being French, is very complex. So the French model take-all by modelling the individual lesion on the individual root. I might suggest that's going a bit far. And then they play with temperature and rainfall to then grow the lesions, alter the root dynamics of the crop. We looked at that and wondered how we could parameterise that for Australian conditions and didn't worry about it. So there are people that have thought about it, but I don't think they've thought about it in terms of maybe a simple damage coefficient. And when we look at the plant pathology literature, what they do is they pull the plant up, stare at it and go, that's a 1 in terms of the damage. And they've had a lot of experience in coming up with 1, and they'll argue between each other about whether it's a 1 or a 2 on a Likert scale. So we're dealing with that, but then taking that through to wheat yield isn't done very often. In fact, it's quite remarkable. But we've been able to do it in nematodes in Queensland for the first time because we've been able to capture what the damage to the root system is in terms of how much water the crop is able to take up. So the process of that damage translating through to a yield loss can now be calculated. We can at least do that with Absent by shearing off the root system and treating disease like a subsoil constraint. So that's where we can go with that as a concept. But this work's still very much in the early stages.
That's all time we have today. So